Now we have the last talk in this morning. Also, a very critical point. Dr. Rafael Juarez and Professor Javier Sanz will give in two parts in the talk. This will be related with very advanced modeling of neutronic, or I will say more, particle transport and the relation with the safety. So this group of Professor Javier Sanz from the Open University and Professor Rafael Juarez is actually the leading group for all the neutron transportation, neutron calculation in ITER. Not only that, but also responsible of many of the aspects in safety induced because of neutron and charged particle in ITER. So they are the reference in ITER for all these calculations with the model system that they will explain to us. So now we start with Professor Rafael Juarez. Please, the floor is yours.
Thank you very much, Manolo. Well, good morning to everyone. I'm going to talk to you about how modeling and licensing ITER has been driving the excellence in 3D particles transport in the last years. We are going to split this talk in two parts between myself and Javier. But that refers to how research works at UNED. We have two main research lines. One is the analysis and design of nuclear fusion facilities, and the other one is the development of computational tools for nuclear analysis.
Excuse me, it seems that, oh, it's okay. Maybe we can put,
Okay.
I'm sorry, but it seems that it was...
Okay, is it better now? Okay, so as I was saying, we have two research lines. One is devoted to analyze and design nuclear fusion facilities from the standpoint of radiation transport, and the other one has to do with the development of the computational tools to do so. And this is a loop that feeds itself. So we find new problems during the design of a facility, and we need to develop new approaches to solve them. So now that we have a new approach, we can face new problems, and this is how the loop works. And we are going to talk to you about how this loop has been especially vigorous during the ITER design for a very clear reason, which is that we have a nuclear regulator inspecting the job we are doing. I'm going to talk to you about the problems, and Javier is going to talk to you about the approaches that were needed to be developed to face these problems. So as I say, this is my first part. I'm going to talk to you about the challenges of ITER related to radiation. I need to include here a disclaimer to say that the content of the presentation is not vinculant for ITER as a nuclear operator in any sense. Okay? What makes ITER challenging at this point is important to make. Although we have had quite a lot of talks about ITER and JET, there is one difference between ITER and the rest of previous facilities that I want to highlight at this point. But basically what happens here is that we have never built anything nearly comparable, and you're going to see why. We tend to compare ITER with JET, which is its predecessor. And we have heard already that it's 10 times larger in terms of plasma volume. Okay, that's already a challenge itself. It will have 30 times more power in a shot. But the key difference is the neutron budget. ITER will operate for long periods of time with respect to JET. And the neutron budget of ITER will be 1.5 million times larger than in JET. So ITER is not only a machine larger than JET, it is significantly more nuclear. Okay? And this is going to make everything totally different. In any case, just to compare sizes, you have in the red circle, you have the workers. So you can see that there is tremendous change in size. But the ITER budget expected is going to be 3 times 10 to the 27 neutrons. This is a huge amount of neutrons that if you could put all together in a bag, that would be 5 kilograms of neutrons. Okay? It's quite a lot of neutrons. Keep in mind that DT neutrons are born with a velocity of 17% of the speed of the light. So they are really energetic neutrons. They are really penetrating. And we need to know where these neutrons go. And that is nuclear analysis and neutronics. We need to track where these neutrons are going and what are the effects derived from all this massive spreading of neutrons in every plasma shot. Okay, ITER is being built. It has been for many years in design, for many more years in construction. And just to give you an idea of the size of it, I wanted to include this picture of the site by 2020, nearly 1 year ago. It's very difficult to appreciate the real size of everything, but I want you to keep just an eye on this building here. This is the tokamak complex. It's a building made out of 3 buildings in reality, and the central one, which is the taller here, is the tokamak building. You can see that this extends a bit beyond to another room here, which is called the assembly hall. This is one of the largest rooms in the world. This tokamak complex is the heart of the site. But it's, as I say, it's difficult to get an idea of how big this is going to be, because even when you have cars here in a parking, you don't get full understanding of the size. So I decided to compare that with Monasterio del Escorial, that you all should know by now. Okay, and these pictures are in the same scale. If you visit the monastery, you will feel that it's a comparable scale in many senses. And I found illustrative to remark at this stage that building the monastery took 21 years to the largest empire of the world. But going into the specifics of what we are going to do, I'm going to explain shortly the physical problem that we are facing when we speak about nuclear analysis for ITER. Okay, and there are 2 main features of it. The first one is that it's a huge facility, as we have been more or less commenting. And the second one is that it will contain, for the first time, many complex, new, and very intense radiation sources in a massive scale that we have never dealt with before. Okay? These 2 separately are challenging, but when you put them together, things get even more complex. Why we say that ITER is complex? Because it's the first massively superconducting and massively nuclear tokamak. Okay? Although there has been previous nuclear tokamaks with some neutrons, it's not the same scale as I was telling you before. The complex itself is very big. It's 120 meters, 80 meters, and 80 meters height. It's heavier than the Empire State Building. It will have 674 classified rooms from the radiation perspective. That means that we need to control, well, we need to design and control so many rooms during the design and the operation of the facility that will get things really complex. There will be over 4,500 penetrations, larger than 10 square centimeters. These penetrations will be across the whole facility. They will host cryogenics, they will host water cooling, they will host optic fibers, laser lights, they will host cable trays, a myriad of systems that will cross the many walls of the facility because it's an experimental facility. We need to put many systems everywhere and we need to operate them. The operation of these systems imply penetrations in every wall. Each penetration will represent a leakage path for the radiation. And we need to put all of them together to detect which is creating which problem to what system. And it's a combination of a huge number. Okay? Plus, the facility will have very thick walls, 2-meter thick walls with steel rebars. Just to give you an idea of how challenging this is, I found yesterday that the Panama Channel doors that close an ocean, they are 2-meter thick concrete walls. Okay? The combination of so many penetrations and very thick walls create a problem from the computational standpoint. Okay? But I will not enter into that, just to tell you why this is challenging. And as I said, there will be thousands of tons of experimental equipment all across the facility, everywhere, massively spread. Okay? Not only the tokamak, that will be a very dense system, but everywhere in the tokamak complex, because each of these systems is high technology, and they need many auxiliary systems to be operated. And there are hundreds of diagnostics, cryopumps, and many other high technology equipment. So there will be a facility full of sensible equipment. Okay? But now it's the problem of the radiation sources. In ITER, there will be 10 radiation sources of relevance. Many of them have been found before in other facilities, but not in the massive scale that ITER will face. Okay? I have located geographically in the plant where each of these radiation sources will take place. The 5 first sources will be inside the reaction chamber. They are related to plasma and systems that operate plasma. All the water-related sources are very spread because the tokamak cooling water system is a huge system that Joaquin was showing before as the US contribution is. We will comment about this a bit later. And there is also the activated corrosion products. Okay? And then there is the fact that when you have a very intense radiation source, a very intense radiation field, in special of neutrons, once you switch it off, you may have an induced residual radiation. And in the case of ITER, it's going to be of relevance as well. What is important to keep in mind that makes ITER so challenging at this stage is that we find many radiation sources outside the bioshield. The bioshield here is highlighted with a dotted white line. And you see that is this circle here. This is the bioshield. We have many radiation sources that transcend the bioshield, and that creates challenges. And the last thing to highlight at this stage is that only the water-related sources, nitrogen 16, 17, and the activated corrosion products, only those sources were found to be of relevance in fission industry. So we need to learn how to handle these radiation sources and how to model them as well, while everything is being built at the same time. Okay? Okay. Putting all these things together leads us to a set of challenges. Just to list them in groups, we know that we need to understand the heating of the components because we need to cool them. And to do that properly, we need to know how the heat spreads volumetrically inside the component, and in specific, the nuclear heating. There will be troubles associated to the biological doses. When they refer to workers, it's something that has to do with radiological protection. But when they have to do with public, that's safety. And we know that we want to sell fusion as a especially safe nuclear power. Okay? We need to protect the electronic because it fails. I'm going to show you how it fails. We need to calibrate this machine. We have never produced such an intense plasma. So there is also the question of how do we measure the power? And calibrating the machine is itself a research line. Okay? And we need to forecast and minimize the radioactive waste stream from the design phase to avoid future problems. Okay? But as I said, all these problems get even more complex because of the fact that we will have a very complex plant with a very complex radiation source. Okay? And what was found many years ago is that the previous techniques to deal with the design were not ready. They were not enough. So new computational technologies were required to forecast the radiation field. And subsequently, new shielding technology were necessary to protect the operation of the systems. We are going to deal only with the first point, new computational technologies to forecast the radiation. And from this point, I'm going to show you a few examples of why we need to take care of the radiation field in ITER. Okay? You're going to see a video here. Before I play it, I want to introduce you that this corresponds to a jet DT shot conducted in 1991. It produced 1.7 megawatts of power. It produced neutrons and photons. And you're going to see for half a minute or something like that, euphoric scientists, because they were going to produce a plasma shot. That was a historic plasma shot. It was in preparation of the shot that Joaquin commented before. At some point, the video is going to focus on a TV. The TV is displaying what a camera inside the tokamak is watching. Okay? And it's going to illustrate you how electronic fails in the presence of radiation.
Nervous faces, intense concentration. the prelude to a countdown to history.
10, 9,
Scientists had been
8,
working towards this
7,
for the last
6,
13 years.
5,
At 5:15 on November the 9th,
3,
they got it.
2, 1, 0.
Fusion, creating energy by smashing atoms together.
Okay, so the Palma pulse lasts 1 second. But what you see is that all the electronics goes blind. It fails. Nowadays, everything is electronic. Everything. And ITER is not an exception. It's full of electronics for everything, in special for safety control. Okay, so if our safety systems depend on not failing under radiation, but we know there will be a radiation field, there is something here that doesn't match. Okay, we need to predict the radiation field very accurately, and we need to protect the electronics accordingly, because everything in ITER depends on electronics, even the safety as well. Okay? Another example of why we need to keep an eye on the radiation in ITER is that, as has been commented a few times already, ITER will be superconducting tokamak. It will have 18 toroidal field coils, 6 poloidal field coils, and 1 central solenoid that will all be superconducting. It will have over 100,000 kilometers of superconducting strand. The field will present an intensity in the peak of up to 14 Teslas. It will operate at 4 Kelvin. This is cryogenic. It's an extreme temperature that requires liquid helium for cooling. Okay? And it will store a huge magnetic energy of 51 gigajoules. This is a tremendous number. This energy is enough to make the machine jump. Okay? And that is not a problem. We can design the machine so it jumps. The problem is that if everything disappears in a second, the superconducting coils might melt down. Okay? And you know, it's a 30 billion project, so if you break it, you pay it. Nobody wants to break it. Yeah? So the cryogenic plant must be designed carefully. We need to understand pretty well how the heat loads are distributed in the coils to look for spots and look for the total amount of heat and mitigate it accordingly. Okay? Another example, when we have a very intense neutron field, like the one that will be inside the chamber, everything will become really radioactive. So when the machine is in shutdown, you may have to enter, not you of course, a robot will have to enter there to do some maintenance of something, like a diverter. That's what Joaquin has been explaining to you a few minutes ago. If we need to do maintenance of the diverter, we need to bring some equipment inside. And that's going to be electronic equipment, and we know, we have just seen the video, how the electronics is likely to behave under very harsh radiation environment. How harsh that's going to be is something that we need to answer. We need to understand how the shutdown field is going to be either inside the machine and outside as well. And that shutdown field is very complex because the activation distribution in space evolves with the gradient of the neutron flux. So it's not the same considering a sphere than a real diverter. And this source is going to distribute it in very high spatial resolution. So here you have an example of how the diverter gets activated with a resolution of 1 by 1 by 1 cubic centimeter mesh, which is already very small. But if we could go smaller, that would be desirable because the predictions change. Okay? We need to understand the activation with a very high spatial resolution. Another example is that you may want to transport this diverter somewhere, in example, the hot cell, because you want to do maintenance to that cassette. You cannot touch it, of course, but you have to bring it somewhere. While you are transporting this activated component, you are going to create a radiation field as well. And that radiation field is going to give you an accumulated dose, again, to the electronics, because it's everywhere. Okay? And not only that, but you will see that in the TCWS. I explained you that later. And the last example that I wanted to comment to you about was the demonstration that the plant is safe. Okay? There is a very demanding and a very rigid nuclear regulator in France, by chance. Luckily, that's the case. They are inspecting everything that it does. And they are asking ITER organization, how do you demonstrate that your plant is safe? They are working against a limit for public exposure that is 1 millisievert per year dose in the fence of the facility. The fence here is in blue. Okay, it's the perimeter that you see in blue. ITER has to demonstrate that the dose beyond the fence is, in any case, much lower than 1.28 microsieverts per hour. Okay? You can see in green and red the actual values computed by today. Okay, so you see that the dose rate level in the fence is between 10 and 100 times lower than the limit. This is very good. This demonstrates that the building that has been already built is safe. So far, calculations is the only thing we can do. In future, we will have to validate our calculations with in situ sources. And eventually, there will be, beyond the calibration, a real demonstration of safety. But so far, this calculation is the only thing we can do. These lines may seem, they could seem naive. I could have drawn them myself. But getting to here took 2 years of work of 6 people full-time plus 2 people part-time and a huge effort. In doing so, to demonstrate it, among other things, we needed to build the most complex MCMP model of the ITER tokamak, and likely the most complex MCMP model in the world. It was so important that it was published in Nature Energy, which is a very, very relevant journal in our field. We used that model to determine the radiation conditions impinging the bioshield. That was considered as a radiation source for a subsequent calculation in the tokamak complex, as you can see in the bottom pictures. Not only that, we needed to construct a geometry model of the building as it is built, because it's built. Okay? That included modeling 7 edifices, the soil and 1 kilometer of air to capture the skyshine. We needed to model 4,500 penetrations, one by one, review them independently, and keep a track that each one is properly modeled, because you don't know beforehand which is going to create a problem where and due to what radiation source. So you have to put everything in, and you need an independent review, because you could fail, humans fail. Yeah? We needed to model all the 674 rooms explicitly, because as I told you at the beginning, there will be the need to control the radiation level in each of the rooms. So first we need to grant that the design is proper, then we will need to monitor the evolution in reality as ITER operates. Okay, and some other shielding measures that it was known in advance that they would be needed. And the last thing, and with this I'm going to finish my talk, we needed to model the radiation source of the tokamak cooling water system. It's a tremendous water system. It is made of over 15,000 pipes. Each of these pipes, each of the pipes will contain a radiation source while the machine is operating. Once it stops, everything will disappear. It's a very short living isotopes. So as Joaquin said, in the case of a spill, there is no worry. But during the machine operation, it's a real problem. Okay? There are over 15,000 pipes. Each of them contain a source term that comes from the previous pipe. Okay? So as the water flows, these isotopes decay. And this very large source and very complex has a time evolution. Okay? And we needed to model every pipe explicitly and account for the activation of each of the isotopes in each of the pipes with a proper time resolution. Okay? And the result has been quite impressive, it's in this picture, but also quite important, because you can see by looking at this source that most of the intensity, orders of magnitude of the intensity, are located in the center. And that center is very well protected. It's in the core of the facility. But the pipes in the perimeter, which have an activation 5, 6, 7 orders of magnitude lower, being at the perimeter and so close to the wall, those were the troublesome ones. Okay? That was not expected at the beginning, and measures were required once that was detected. Okay? So that is the end of my part of the talk. So I just wanted to highlight how modeling and licensing ITER is pulling from the development of the nuclear analysis toward a level of excellence in 3D that we have never seen before. Okay? So now I give the stage to Javier.
Okay. Pues now I'm going to tell you a story for which we can set its beginning, let me say, about 10 years ago. At that time, ITER needed to know nuclear responses with a very high resolution and very high accuracy, as Rafa has shown in defining all the programs related with ITER. The neutronics expert, I mean, they were the people in charge of providing all these nuclear response results for any nuclear or any radioactive facility. Is now okay? Oh, now okay. I say that the neutronic expert, I mean the neutronics people, were the people in charge of providing these nuclear responses results for any facility, for any nuclear facility. What was the conflict? And here is the conflict. At this time, these people didn't know how to do it for ITER. Not at all. They didn't know how to do it. And the main objective of the presentation is just to show how this conflict has been overcome gradually until today. On the other hand, if there is a story to tell, is because there are a lot of people that has made a great job, people from laboratories, universities, and companies, mainly from China, Japan, USA, and Europe, just contributing to all this area of the computational neutronics for ITER. And in this frame, I want to show what is the second objective of the presentation. It's just to show that Spain has been a very important actor in the development of this story. In fact, mainly because of the UNEF activities and the collaboration and really hard support of CIEMAT on all these activities. In the Rafa's talk, we have shown what are the key neutronics questions asked by ITER then. And also in the Rafa's talk, we have, Rafa has revealed really what has been the ending of the story until today. And it's really a pretty happy ending. Now, neutronics people can provide to ITER Kufin's question, something totally impossible, not long ago, no more than 10 years. So let's see in the presentation to show how all this achievement has been accomplished. But before that, let me say that in the rest of the I'll give the rest of the presentation in Spanish just to save time for question. The slides will be in English, and in fact, the slides will be very dense to make easy that the presentation can be followed by our speaking audience and our close friends. Esta es la estructura de la presentación. A título introductorio diría que el análisis neutrónico en ITER se resume en saber abordar dos problemas generales: saber hacer cálculos de transporte y saber hacer cálculos de transporte acoplado a transporte de radiación, pero bajo condiciones muy exigentes, como bien ha comentado Rafa, geometría muy compleja, fuentes muy complejas, y además hay que conseguir resultados con una alta resolución espacial y una alta exactitud. Para ser exitosos en esta tarea necesitamos tres tipos de productos bien cualificados. Primero, códigos de transporte, códigos de activación y sistemas que les acoplen adecuadamente. Segundo, datos nucleares. Y tercero, modelos geométricos lo más reales posibles. En esta presentación Explícitamente solo voy a tratar el primero de los productos. Y la primera pregunta que nos podemos hacer relativa a estos productos es: ¿por qué tipo de códigos optar? ¿Códigos deterministas o códigos de Monte Carlo? La contestación para ITER es clara: códigos de Monte Carlo, debido a la complejidad geométrica, la enorme complejidad geométrica que os ha explicado Rafa. Aparte, hay otra serie de ventajas de utilizar el código de Monte Carlo que expongo aquí y que todas derivan de lo que ya bien ustedes saben. Monte Carlo es capaz de tratar todas las variables implicadas en el transporte de forma continua. Y que esas ventajas las resumo en este. Perdona, es que he pasado si es. Ay, Dios. Perdonen. ¿Pero qué es esto? Perdonen, la resumo en esta frase. La exactitud en los cálculos de Monte Carlo solo van a ver afectados por una cosa, por la incertidumbre estadística del propio método. El problema, ¿cuál es? Que para conseguir muy buena estadística hay que a veces gastar muchísimo tiempo en los cálculos. Y este es el primer punto de la presentación: cómo hemos logrado acelerar los cálculos de Monte Carlo para transporte. El segundo tema de la presentación tiene que ver con ver cómo en la práctica los códigos de Monte Carlo son capaces realmente de tratar geometrías 3D reales tan complejas como las de ITER. Y el tercer punto de la presentación será ver hasta qué punto los códigos de Monte Carlo son útiles para poder llevar a cabo cálculos de transporte acoplado, cálculos acoplados transporte-activación. Y vamos a entrar ahora ya que me familiarizo. Pero esto es enormemente sensible. A ver. Ahora, bien. Al primer punto de la presentación, que es los métodos para acelerar los cálculos de transporte. En esta transparencia solo quiero comunicarles 3 ideas básicas sobre Monte Carlo antes de pensar más en detalle. ¿Cuál es? Pues que el método de transporte de Monte Carlo se basa, y quiero que vean, simplemente en simular el proceso de transporte para neutrones individuales, desde que nacen hasta que mueren, y que en cada historia lo que tenemos que hacer es computar el valor de una variable aleatoria, que llamamos que es el estimador de ese observable físico que es de nuestro interés. Pues bien, la media de ese estimador, o lo que es lo mismo, la media de los valores que obtendrían si de un número infinito de historias que quisieran simular, sería el valor de ese observable físico. La segunda idea es que la realidad del Monte Carlo solo se va a poder correr, déjenme decir así, con un número finito de historias. ¿Y qué tipo de resultados nos dará? Pues nos dará la media de los valores de ese número de historias finito que hemos corrido, y que ese valor será el estimador de la media real, el valor del observable físico. Y el otro resultado que nos dará será el error precisamente de esa estimación. ¿Y cuál es la tercera idea que les quiero comunicar en esta transparencia? ¿Cuál sería el modelo más directo, más sencillo para crear un modelo de Monte Carlo para transporte? Pues el que llamamos modelo análogo, que sería simplemente que asignar a los procesos que va a experimentar nuestro neutrón durante su vida las funciones de probabilidad reales de la naturaleza, las que nos dicta la naturaleza, que saben que el transporte es per se estadístico. Y luego simplemente computar el valor del estadístico correspondiente a nuestro observable físico, ya tendremos el resultado. ¿Cuál es el problema? De que este estimador, déjenmele llamar estimador natural, tiene una varianza muy grande, una incertidumbre muy grande, lo que hace que el método de Monte Carlo análogo tenga una aplicación muy limitada. Y esto me vale para entrar directamente ya, vamos a darle muy despacito, a lo que es qué se ha hecho en los últimos años para acelerar los procesos de Monte Carlo. Y aquí quiero en esta transparencia introducirles 3 ideas. Una, hemos logrado crear métodos de Monte Carlo no análogos que han logrado acelerar muchísimo los cálculos. ¿Qué es un método de Monte Carlo no análogo? Déjenmelo decir rápidamente. Pues ahora lo que utilizamos son funciones de probabilidad no naturales, con estimadores consistentes, cuya media sí que será el valor de nuestro observable físico y cuya varianza, y aquí es el punto importante, va a ser mucho más reducida que la de nuestro estimador natural. Y esto lo hemos logrado, ya lo logramos hace 10 años, ¿para qué? Para hacer cálculos en zonas muy localizadas. Ese era nuestro Monte Carlo hace 10 años aproximadamente. ¿Qué hemos logrado durante estos últimos años? Pues hacer eso extensible a poder realizar cálculos en muchas más zonas y sobre todo en zonas muy amplias, tanto como todo el reactor. Ahora somos capaces de obtener distribuciones de nuestras respuestas nucleares con mucha precisión a lo largo de todo el reactor. Es lo que llamamos cálculos globales. Decirles que esto se ha obtenido gracias a los que denominamos métodos de reducción de varianza global. Con ellos obtenemos los parámetros de reducción de varianza que utilizamos en nuestros modelos análogos para llevar a cabo estos cálculos globales. Rápidamente decir que estos parámetros globales de reducción de varianza se pueden obtener por dos vías, una por vía Monte Carlo y otra por vía determinista. Vamos a dejarlo ahí, sin más detalle ya comentarlo. Segunda idea que quiero transmitirles en esta transparencia es que otro elemento que ha contribuido enormemente a acelerar nuestros cálculos ha sido la utilización de la computación en paralelo. ¿Y por qué? Pues porque el método de Monte Carlo ya es intrínsecamente paralelo. Y ahora, la tercera idea que les quería comentar es que hemos logrado una eficiente combinación entre la computación en paralelo y las técnicas de reducción de varianza global, habiendo conseguido de hacer que Monte Carlo se pueda utilizar de forma práctica para resolver los problemas de ITER. En la UNED, así de forma muy rápida, en relación a los temas de transporte, decirles que nuestro código de partida básico ha sido el código MCNP, eso sí, al que hemos hecho muchísimas modificaciones, de tal forma que ahora tenemos un código que podemos llamar MacUNED. A lo largo de la presentación les iré presentando las modificaciones más importantes de las que les quiero hablar. Y luego ya muy rápidamente decirles que en cuanto al tema de aceleración, pues la UNED está utilizando computación en paralelo y las técnicas de reducción de varianza global, que las obtiene por vía Monte Carlo y utilizando procedimientos bien establecidos en la bibliografía. No ha introducido nada novedoso al respecto. Ahora ya vamos a entrar al segundo de los temas, que es el de la geometría. Decirles que hace 10 años, pues los métodos de Monte Carlo, los códigos de Monte Carlo más potentes, y en definitiva, déjenme decirme, MCNP, era perfectamente capaz de tratar geometrías complejas en 3D. ¿Cómo lo hacía? Pues a lo que vi. ¿Cómo lo hacía? Pues utilizando la metodología CSG. Rápidamente ya saben lo que era subdividir todo el espacio físico en regiones volumétricas que podían construirse a través de cualquier superficie de primer y segundo grado. ¿Cuál era el problema? Que a medida que la geometría se hacía más compleja, la construcción de los modelos se hacía siempre tediosa, los que hemos trabajado en Monte Carlo desde hace muchos años, ya llegaba a ser desesperante y con ITER imposible de realizar. Ante esta situación, ¿qué solución se propuso? Pues la alternativa que se propuso fue tratar de utilizar modelos CAD en los cálculos de transporte de Monte Carlo. Y se propusieron tres metodologías. Una, que vamos a llamar de conversión, ¿en qué se basaba? En querer pasar el modelo CAD a un modelo CSG, ya directamente utilizable por el código de Monte Carlo. Otra segunda, que podemos llamar directa, se basaba en ¿qué? En tratar de utilizar directamente el modelo CAD. Y otra tercera se basaba en utilizar una geometría descrita ya en malla no estructurada. La más madura con mucho es la primera y es la que con mucho más se ha utilizado en ITER. Y ya centrándonos en esta metodología, esta transparencia que voy a ir muy rápido, solo por detalle, si ustedes quisieran seguir todo el procedimiento desde que le dan un modelo CAD de ingeniería de un componente hasta que le introducen en el modelo global de ITER para construir el modelo de transporte que van a utilizar en los cálculos neutrónicos, tendrían que seguir todos estos pasos. Solo voy a llamar la atención sobre el último, el más importante, que es la conversión del modelo CAD debidamente preparado, aquí eso indico lo que es debidamente preparado, ya a un formato CSG directamente utilizable por MCNP o el código de Monte Carlo correspondiente. Para hacer esta etapa se necesita obligatoriamente un software nuevo que había que construir. Y ahora, ¿qué se ha hecho en la UNED relativo al tema de geometría? Bueno, pues hemos optado por déjenme decir, la metodología de conversión. Hemos utilizado prácticamente en el 99% de los casos el código MCAM, que es el código de referencia en ITER y el más consolidado en el campo, pero tenía un problema, o tiene un problema, que es open source. Entonces, lo que hemos hecho a UNED ha sido desarrollar un código de conversión que hemos demostrado que tiene las mismas capacidades que MCAM y que en los últimos trabajos ya hemos utilizado, algunos de los que ha presentado Rafa, de algunos de los problemas que ha presentado Rafa. Otros dos problemas que hemos tratado en relación, que tienen mucho que ver en relación con la geometría, han sido, uno, ver cómo la geometría, las necesidades de memoria para almacenar la geometría se podían reducir, y también ver cómo las necesidades de tiempo para inicializar esa geometría se podía ver reducida. Y otro tipo de problema ha sido el de analizar algoritmos que permitieran tratar la geometría almacenada de forma que pudiéramos hacer mucho más eficiente el proceso de retracing y, como spin-off, por estar muy directamente relacionada, el proceso de visualización de esa geometría. Los resultados han sido buenos y tienen bastantes implicaciones prácticas. Les voy a decir una. Ahí les doy algunos datos de tiempos, pero lo importante es que muchos de los problemas que ha presentado Rafa, déjeme decir, con el modelo C-Model, ese es el modelo global de la estructura de ITER, no se podrían haber realizado si no es gracias a estas modificaciones de las que estoy hablando, que MCNP no tiene. Y es más, el modelo Light, ese del que ha hablado Rafa, que han publicado en Natural Energy, si no hubiera sido por estas modificaciones, no hubiéramos podido hacer ningún cálculo con él. Vamos a ir a continuación al tercero de los temas de la presentación, que es el de cómo resolver el problema de transporte acoplado, transporte activación y fundamentalmente resolver el problema más importante dentro de este campo, que es el de calcular dosis residuales. Déjenme decirles rápidamente que hace 10 años, cómo se hacía este problema en comparación con lo que se hace ahora, no tiene prácticamente nada que ver. Entonces, este problema, el cálculo de dosis residual, déjenme decir que, antes de nada, ¿a qué llamamos dosis residual? Pues es la dosis debida a los fotones que emiten los nucleidos radioactivos. Y como bien saben, estos nucleidos radioactivos van a seguir estando presentes aunque la fuente de neutrones esté apagada. Y para resolver este problema conceptualmente se pueden concebir tres etapas. Una primera, que es la del cálculo de transporte neutrónico, en la cual obtendremos los flujos. Una segunda, que será el de los cálculos de activación a partir de los flujos anteriormente obtenidos y en el cual obtendremos la fuente de desintegración. Y una tercera, en la que transportaremos los fotones de desintegración y obtendremos lo que vamos buscando, que es la dosis residual en aquellas posiciones de interés. Como os dije, esto hace 10 años se trataba de forma embrionaria y ahora ya se han propuesto dos esquemas de computación para abordar este problema. Uno de ellos es el que denominamos R2S. ¿Y en qué consiste? Pues en este esquema se utilizan códigos de transporte, códigos de activación que se combinan de forma adecuada. ¿Y qué se realiza? Se realizan las tres etapas de cálculo que les he mostrado antes, todas de forma independiente. ¿Vale? Para transporte, ¿qué utilizamos? Códigos de Monte Carlo. Y para activación, ¿qué utilizamos? Pues para activación utilizamos códigos de inventario lo más completos posibles. Y casi está. Aquí quiero recalcar la idea más importante del esquema. Con este esquema somos capaces de capturar toda la física del problema y de forma completamente rigurosa. Y además el sistema es aplicable a todo tipo de sistemas. ¿De acuerdo? Ahora bien, hay un factor, una característica inherente del método que hace que limite su exactitud para algunos casos. ¿Y cuál es esta característica del método? Pues el que obligatoriamente los cálculos de activación se tienen que hacer discretizando el dominio espacial. ¿Esto qué significa? Pues que en sistemas en los que haya regiones que tengan el flujo unos gradientes muy pronunciados, puede hacer que el grado de exactitud pues, se vea bastante deteriorado. Y lo que han hecho los distintos métodos que han implementado este esquema ha sido precisamente el intentar aliviar este factor limitativo, pudiendo decir que a día de hoy está muy resuelto. Aquí les pongo los cuatro métodos que se han ido utilizando para implementar este esquema. ¿Y qué hemos hecho en la UNED? Pues en la UNED lo que hemos hecho ha sido nuestro propio R2S. El R2S UNED consta para transporte del código MAC-UNED y para activación del código ACAP, que también es propio nuestro. Y comentarles que en nuestro sistema tiene algunas características muy específicas que le han hecho especialmente atractivo. Voy a comentarles aquí solo una, que es la de haber introducido la técnica Zelander-Voxel, o déjeme decir, evaluación de resultados por porciones de Voxel, elemento de malla. ¿De acuerdo? ¿Y en qué consiste? Pues lo que nos permite es que ahora podemos dar resultados de flujos o de cualquier otra respuesta nuclear en porciones de voxeles, considerando en cada porción el material de esa porción y el flujo que realmente ve esa porción de material. MCNP solo puede dar cálculos en malla, en voxel, pero utilizando flujos promediados. Esto tiene muy importantes consecuencias y ventajas prácticas. Les voy a decir una. Con el R2S UNED podemos hacer cálculos con la misma exactitud con la que se conseguiría utilizando un modelo en malla, un modelo ideal en malla no estructurada. ¿De acuerdo? Bueno, aquí les pongo otras ventajas y otras capacidades que hemos introducido diferenciables de otros sistemas que, si quieren, luego podremos comentar. Vamos ahora al siguiente esquema computacional que se ha utilizado para resolver estos problemas. Y es el que denominamos como D1S. Para entender bien la idea en la que se basa, quiero antes recordarles que recordemos un momentín qué es lo que hace un código de transporte estándar. Y lo que hace es simular el transporte de neutrones acoplado al de fotones producidos por reacción. ¿Qué queremos hacer en el sistema de D1S? Pues tener un código de transporte que lo que haga sea hacer un transporte acoplado de los neutrones con los fotones emitidos por los nucleidos radiactivos producidos. ¿De acuerdo? Este esquema computacional es completamente exacto para sistemas en que los radionucleidos dominantes cumplan la siguiente condición. Su actividad debe ser linealmente dependiente de la tasa de producción. Esto básicamente esto se cumple pues, cuando los radioisótopos se producen por cadenas de formación en las que solo hay implicada una reacción nuclear y cuando el efecto de quemado es despreciable. Como ven, este sistema no es de aplicación general y por lo tanto exige una fase de preanálisis en la que se realizan cálculos de activación. ¿Para qué? Pues primero para analizar si se cumplen las condiciones en las que se fundamenta el esquema. Y la segunda, si la respuesta es afirmativa, ver los radionucleidos dominantes y ver las reacciones de activación por las que se producen. Esa información se da al código de transporte para hacer la simulación correspondiente. ¿Qué ha hecho la UNED respecto a este esquema? Pues hacer su propio D1S UNED. El módulo de transporte, el código de transporte en sí mismo, está integrado dentro de lo que es MAC-UNED y los cálculos de preanálisis de activación se hacen con el código ACAP. Se han introducido muchas capacidades diferenciables de otros y de mucha aplicación práctica, y es lo que ha hecho que el código DE1SUNED sea el código de referencia adoptado por ITER para realizar todos los cálculos de dosis residual. Déjenme decir rápidamente que ese conjunto de capacidades nuevas que tiene DE1SUNED se pueden estructurar en 3 bloques. Uno primero, en el que nos permite pues, obtener la fuente de desintegración gamma, el transporte de la misma y todas las respuestas nucleares correspondientes. Una segunda, y muy importante, que nos va a permitir el entender la física de lo que está ocurriendo, identificar los mecanismos, el por qué se producen las dosis en las regiones que nos interesan. Capacidades que son extensibles absolutamente a todos otros tipos de respuestas nucleares, aunque sean en cálculos de la fase de irradiación. Y un tercer bloque es el que nos ha permitido tratar de manera muy flexible y relativamente fácil muchas situaciones que se dan en ITER y que luego, si quieren, las podríamos comentar. Aunque solo haya dejado un párrafo aquí, como es obvio, lo que son la cualificación de métodos es clave. Y solo comentaros que R2S y DE1SUNED han participado en todas las iniciativas que se han lanzado para cualificar códigos, tanto para ITER como para demo. Y los resultados han sido bastante buenos. Aquí simplemente, después de lo que ha dicho Rafa, como ya habíamos visto, es que el tema de fuentes, saber modelar fuentes, es crucial para tener una neutrónica de ITER confiable. Aquí esta transparencia solo vale para recalcar el hecho, hay que saber modelar fuentes y hay que saber muestrearlas bien, para que luego nuestros cálculos de transporte puedan ser confiables. Aquí resumo las fuentes de las que ha hablado Rafa anteriormente. Ya vamos a entrar en el último apartado de la presentación, que es el de resumen. Con esta transparencia podría resumir todo lo que he hablado, pues porque representa todo el proceso de cálculo neutrónico y de análisis que hoy se está utilizando en los análisis de ITER. Y ahora podría pasar a comentarla, pero no lo voy a hacer. De hecho, lo que querría es que los interesados la comentaran y me lo mandaran por correo electrónico. Estamos en un curso y yo estaría encantado de recibir sus comentarios, de hacer un feedback con ustedes, y si algunos además están interesados en trabajar en alguno de los temas que de forma muy rápida les he comentado, estaríamos encantados en ayudarles. Y simplemente lo que voy a indicar, déjame hacer unas sugerencias para hacer, si se animan a hacer este comentario. Una, es que sepan que partimos de lo que les hablé antes, modelo de ingeniería CAD de un componente o varios componentes que habría que introducir en ese modelo global de la estructura ITER hasta obtener el qué, pues un modelo integrado para transporte. Con él ya podíamos empezar a hacer los cálculos de transporte. ¿Qué hay que hacer para llegar de aquí a aquí? Eso es lo que les pido que si quieren puedan comentar. Y la siguiente fase, ¿cuál sería? Pues a partir de este modelo, obtener para la fase de irradiación, en definitiva, cuando la fuente de neutrones está encendida, todos los resultados asociados a la misma, haciendo que, eso es lo que pues, estaría encantado de que me pudieran decir, y lo mismo para la fase de posirradiación. Ahora apagamos la fuente de neutrones y para los resultados asociados a la fase de posirradiación, ¿qué habría que hacer? ¿Qué alternativas podríamos utilizar? Y por último, ¿qué habría que hacer en el comentario? Pues que también me dijeran lo que se ha hablado, qué capacidades tendríamos que utilizar para entender la física de lo que está pasando, para identificar los mecanismos que nos tienen que explicar esos resultados de los que os he hablado en la fase de irradiación, en la fase de posirradiación. Por último, la última pregunta que les pondría, si me apuran, en el examen sería, bueno, ¿y todo este ciclo de cálculo podíamos realizarle con una licencia de MCP y software español exclusivamente? Pues yo diría, inténtelo decir si sí o no, como se dice, y justifiquen la respuesta. ¿De acuerdo? Bueno, y ahora sí que ya para acabar simplemente darles 4 ideas. La primera, como bien antes comentó Rafa, ITER ha sido vital para construir una nueva neutrónica computacional. Esa nueva neutrónica computacional, ¿qué nos ha permitido? Pues dar resultados de nuestras respuestas nucleares con una altísima resolución y con una altísima exactitud para geometrías muy complejas, ITER y todo lo que podemos hacer con ello. La tercera idea es que si me preguntaran cuáles han sido los dos desarrollos computacionales que más efecto han tenido en el desarrollo de la neutrónica de ITER, yo les diría que MECAM y DE-UNES-UNED, opinión que es en general compartida por toda la comunidad de neutrónica de fusión. Y por último, como cuarta idea, decirles que España es un actor muy relevante en dos campos, en el campo de desarrollo de neutrónica computacional y en el campo de las actividades de análisis y diseño de ITER, haciéndolo en varias instituciones, CIEMAT, Instituto de Fusión Nuclear y UNED en este último campo. Y aquí acabaría, solo intentaría hacer un mínimo comentario, introducirle, es decir, Manolo ayer, cuando comenzó el curso, les dijo, se va a hablar de muchas cosas, quiero que capturen una cosa importante, que identifiquen cuáles son los retos de ITER, los retos que hay en la fusión, y les entienda. Habrá muchos más detalles, pero intenten eso. Aquí yo a lo mejor me he extendido en cosas, pero sí que hago míos sus palabras. Intenten capturar eso, identifiquen los retos, y barriendo si me dejen para casa, quiero que vean que la neutrónica computacional es otra tecnología más de la fusión. Y que los retos de la tecnología de la neutrónica computacional son retos de la fusión. Y cuanto mejor neutrónica computacional podamos hacer, ¿qué va a ocurrir? Que mejores plantas de fusión podremos diseñar. Plantas de fusión que podrán ser mucho más confiables, tendrán muchos riesgos, muchos menos riesgos, serán más óptimas y, en definitiva, ¿qué nos van a permitir? Por lo que queremos conseguir, hacer de la fusión una fuente de energía. Os digo esto porque a veces la neutrónica computacional parece que no es una tecnología, que material es una tecnología, o aquí hay muchos círculos en los que hay muchas tecnologías. Esta también lo es. Vean que hace 10 años no sabíamos qué hacer con ITER. Vean que ITER, a la hora de licenciar, ¿quién le tiene que decir qué pasa o no? Pues métanla en su cabeza como una tecnología más de la fusión. Y ahora sí que muchas gracias por el tiempo y por toda su atención.
Come here. Well, let's come here, Javier. Come here. I am really proud of both of you. The first person I had as doctor in my life, Javier. And Rafa is also a PhD student, doctor with Javier and myself. So I am really very, very proud because you did, as you mentioned now, Javier, in the last part of the presentation, a tremendous work. This is a real technology, Without these tools, no way. So, great work. Open University did a tremendous work. Now we are coming together because Javier and Rafa are also members of the Institute of Nuclear Fusion, Guillermo Velarde. So we now combine everything. Maybe you have questions? No, I have one. Mike, you have one?
Fantastic presentation, and I think this is probably, without a doubt, the best in the world in terms of the ability for the safety analysis and so on. So great credit to you, absolutely. Do impurities in the materials come into play at the levels of neutron being released? That's one question. The other question is, what is the most difficult challenge in going from CAD to computational matrices, and what are the lessons learned, I think, out of that? And then one last question. Do you have enough nuclear data? Are you finding gaps where you need cross-section or scattering or, so on? Okay, my 3 questions.
Impurity.
Thank you, Mike. Thank you very much. So I take the first one about the impurities. The impurities in ITER are being considered from the perspective of shutdown dose rate. They are not a challenge with the perspective of radioactive wastes, because the fluence is not expected to be tremendous. So the original purpose of Eurofer, which is oriented to waste management, is not present in ITER, and that's the reason why ITER is not built of Eurofer, but of 316 LN, ITER grade, so-called. ITER grade, that surname refers to low cobalt content for certain dose rate reasons, basically low tantalum and low cobalt. But they are levels easy to achieve, relatively easy in the fission industry. So there is no special, there is no big deals. It's 0.05 cobalt content, 0.01 tantalum content, and that's everything they need to limit for impurities. Yeah.
The second is CAT, and regarding with the CAT. Yeah, okay. Regarding with the CAT, probably the most difficult is just to clear the engineering CAT model. Normally, the engineering CAT model have a lot of, let me say, no mistakes, but solids are overlapping and so on and so on. And this kind of work has to be made manually in a CAT platform. Space scaling is in our case. Just I talking about ITER. Then another activity that we have to do is to remove SP lines, you know, all the surface that have an order above the second one. But this is not for ITER a big challenge. Has to be also done with manually with a space plane or another CAT, motor CAT, and no more. This is the reason why using the conversion methodology, the translational methodology, is very useful in ITER. But for accelerators, this is another issue. Accelerator is another issue. So basically, it's the first part, the most tedious part now, is just to clear the engineering CAD model. Of course, if you say to the engineers, please give me a clear model, no problem, and can be done, of course. And the other question, Rafael.
No, nuclear data.
About nuclear data. Nuclear data. 10 years ago there was problem, but in fact, just in Europe, there has been special dedicated programs for that, and really enough money has been done. And I think for ITER, no, there is no real problems. Even, yeah.
I have one more question. Will the data you get, you're comparing to data from measurements at JET, and I guess JET is going to fire in the next couple of weeks. Is that all of the data you need, or might you go back to your favorite facility, NIF, for measurements there, you know, for confirmation or validation?
JET? Sorry, you have time.
Thank you. So the nuclear data, I guess you're referring to DT nuclear data, or all sorts for the transport?
Skyshine.
Yeah. Okay.
Dose rates.
We are relying on verified nuclear data libraries like Fendel 3.1, and we follow their evolution. And this is just following a recommendation by the IAEA, the International Atomic Energy Agency. And with respect to activation, they are following EAF, made at UKEA, many acronyms here. But in principle, there has been no major gaps identified, but with DPA. Only just DPA, you know, it's a tricky quantity in itself, and computing it through a cross-section requires some thinking. And there are some isotopes for which DPA's cross-sections are not well validated, and they lead, well, not validated, sorry, not well computed, and they lead to negative DPA's values. Okay, that is a clear problem. It's unphysical. But there are no so many others have been identified as major problems so far.
In fact, Mike, in my opinion, the major source of uncertainty, just for ITER, you can use the ONS, so no problem. Because really ITER, let me say, is very suitable for the DONS. Another history is what happened with them. In fact, the only difference of demo regarding with ITER is just the long fluences. So we know that for some problems, the DONS will not be used, cannot be used for that. So we had to, in this case, to go to R2S, and you have the problem of the discretization of the space domain just for the activation calculation. And in this case, we can have some problems. That we have solved with our R2S. I know I don't want to enter more in this, but in this case, is what I bring this issue. In all the R2S systems, you are using multi-groups activation cross-sections, and you are using multi-group neutron fluxes, and this is another problem. In our case, we don't have to use multi-group neutron cross-sections, and we don't have to use multi-group activation cross-sections, so we remove this problem. So the problem is not because of the cross-activity of data, it's how you use the activation data. And in fact, I have at the end of the class, the guy that has introduced this enormous modification to R2S just to deal really in a continuous way the nuclear data and the fluxes for activation calculation. It's Javier over there. No, this will really make a big difference. In fact, now, due to these developments, I think the current neutronic computational capabilities can be extrapolated directly to demo. We don't have to do almost nothing.
Okay. Okay, thank you very much for your presentation. It has been really, really great and very illustrative. And just to have an order of magnitude, imagine that tomorrow ITER says, okay, we have changed the layout of these pipes here for the Tokamak cooling water system. How long will it take just to do everything? Okay, you have the CAD model of these new pipes, and until you have the results at the end. How long would it take? And how many processes do you have to do by hand, and how many of them automatically?
Thank you. So Thank you, Francisco, for the question. So what I showed was made for the first time, so I can tell you exactly how long it takes. It took us 2 years, and in part because we needed to automatize most of the things. They were not ready to be automatic, so you can chain by hand the activation of 10 pipes, but you cannot do that for 15,000 pipes. So we needed to script different operations in CAD software first, and then in dedicated software made specifically to do that. But that's it, 2 years more or less, since we have the CAD model. The general workflow is what Javier has shown before. Is you start in the 3D CAD, simplified, translated, and well, maybe you want the students to answer you, so I'll stop here. So
No.
Then you do once you have the model, you do the radiation transport. With that data, you can compute the activation, and then you eventually, after many different steps, you reach the decay gamma source. Yeah. Yeah. No, if it is changing 10 pipes, there is no problem. Yeah. So, okay, if you omit the geometry-related part, okay, running these things in general, the full line that I showed, it took 5 million CPU hours, which is a huge number, and most of it was spent in the TCWS, in the water source. So I would say at least 3 million CPU hours. Then if you have a massive infrastructure, you can run that in a couple of months. Okay, that's it. Plus the human time, that is 1 or 2 weeks. Okay, but it's, as you can see, it's a heavy expenditure in computers. Okay, and that's why all these developments that Javier was mentioning are so important, because there is the natural trend of solving a problem by adding something. That's called the additive solution. Okay, it's the easiest thing. There is the trend that if you have a computational problem, okay, you can go and buy a bigger computer, but that's really expensive. And what many of my colleagues have been doing is spending the time and spending the efforts to optimize the codes. So they are making saving of an 80% of the computation load. That means that you are multiplying by 5 your computational load for free. The computers we are talking about are 100 million computers. Okay? It's very expensive one. Multiply them by 5 is the budget of, I don't know, 1 million euros, 1,000 million euros, something like that. So just changing the codes have saved quite a lot of money. Okay?
Okay, I want to remind all of you that these systems are applied to ITER, but they are being applied to IFMIF-DONES. They were not this last development, but they were, in general, in the very beginning, applied to the Hyper project, not this D1S or that, but so the experience with different facilities using this code is not ITER only. It's ITER plus IFMIF-DONES plus the S3 project, Hyper, laser fusion, for 10 years working from 2008 to 2017. So many other facilities. And going to this, and this will be the last one, but I want that you talk a little bit about the charged particle transport, because you have incorporated that, and that is very important because when you try also to design accelerators, this model could be useful. They have been useful. When you try to design, which is the safety consideration in the design of accelerator and in our lives now, there are many cases where we need to know the safety consideration of simple, medium, large accelerator. This system are able to catch the answer. So just the last one, Rafa.
The thing is that I have told you about the R2S, D1S for neutronics. In this case, the source is a neutronic source. We, in fact, probably around, let me say, 3-4 months ago, we have a MacuNet that integrated also deuterons or any other light particle also as a neutron source. It's the only, let me say that, but it's true, it's the only system that can do that. And in fact, for IFMIF-DONES, could make easier the calculations in orders of magnitude. Because in this way, you can compute the transport of deuterons, of the neutrons that are induced by the deuteron reactions. Also, the photons induced by reactions by deuterons and neutrons, but this is important. Transport of photons produced by radionuclides, produced by deuterons and neutrons. I mean, we have a D1S for neutrons and deuterons. This means that all the safety, all those rate maps for post-irradiation period in IFMIF-DONES can be done probably, I don't know, but probably 1 order or 2 orders of magnitude shorter than with any other possibility, with the other system. In this case, no, it's Javier, it's another people that they finish this. I want to tell you, if you are interested in all this topic, that Patrice Sauvan is the leader of our group doing all these developments. You can send me an email or whatever you want.
Okay, so thank you very much.